We are now finishing our course with Chapter 13, our last official chapter. We're going to start with slide number 127, and that is this one here titled Populations as the Units of Evolution. On slide number 127, there's a definition of a gene pool. Now, technically, a gene pool is just all of the genetics within a given population. So at the beginning of the course, I often give an example of the country of Iceland, where in that small country, since people don't migrate much from here to there, we have pretty much a group of population there in Iceland that's limited in terms of their genetics. Basically, that population has become their gene pool. So it's all the genetics in that given population as a gene pool. Now, the textbook is going to go into describing two kinds of wildflowers, one red one white one. And what they're going to do here is teach you how to analyze a gene pool. So that's what we're going to do. Now, here's the red flower, the white flower. And then we're going to take a formula. Now, this formula is found in your textbook, but first, here's the name. The name of that formula is called the Hardy-Weinberg principle. So the Hardy-Weinberg principle. And that Hardy-Weinberg principle is called P squared plus 2PQ plus Q squared equals 1. Now what that formula says is that 1 at the end is 100% of whatever's in that gene pool in terms of their genotype, their genetics. So the Hardy-Weinberg formula is P squared plus 2PQ plus Q squared equals 1. Now notice the first bullet on the slide we're on. It says genotype frequency, but it assumes that the gene pool is stable. So this formula cannot work if you're always having a revolving or evolving change. This gene pool must be a snapshot. So it must be a snapshot at a given point. So let's look at an example. So on page 258, so page 258, here we have a story about the red flower and the white flower. Yes, it is the same as the picture shown here on page 258. And what the Hardy-Weinberg principle says is, what is that genetic frequency? What are the odds of certain things happening in terms of math? So the way we do this is you have to be given certain allele frequencies. So the information you see at the top for P and the information you see for Q, the capital R, the little r, that has to be provided to you as a math. That means somebody has done the evaluation, and this is what they found. For P, they found 0.8, and for Q, they found 0.2. Now, of course, we have the sperm, which is the male part, and we have the eggs, which is the female part. Now, what they've done is basically a Punnett square. Remember, in a previous chapter, we had Punnett squares before. So this is basically a Punnett square on steroids. And what we have here is a frequency of P for the capital R, frequency of P for capital R, which was 0.8. So when we do our Punnett square, as usual, a capital R is going to give me two capital R's. Now what I do with my math is my P squared, which is P times P. So 0.8 times 0.8 will give me 0.64. That's how this first box comes about. So P 0.08. Okay, so this P equals 0.8, and this P over here, 0.8, that gives us our 0.64. Then over here, in the next box, we have the capital R, little r, very much like the Punnett square business we did before. So capital R, little r, and that this time it's going to be P times Q. So P times Q will give me 0.8 times 0.2, which is 0.16. Then we do the bottom one here. Again, we do the capital letter first as standard, just like we did with the Punnett square before. So the capital R, little r. And again, that math is going to be 0.8 times 0.2, which will give me again 0.16. So it's the same as this box, the same as this box. Now the last box over here in our Punnett squares are two little r's. The little r, little r. And here I get a q of 0.2 times q, also 0.2, which gives me 0.04. So 0.2 times 0.2 will give me 0.04. Now if I look at all of these boxes and do the Hardy-Weinberg, I notice that I already have my p squared. So that's the p squared earlier, 0.64. I also notice I have a pq and another pq, but the second half of the formula says 2 times pq. So I'll have 2 times this value, which is 0.16 times 0.16, which is going to give me 0.32, because I have 2 of those, so 0.32. The last one is simply q squared. Q squared is equal to 0.04. Now if I were to take all these numbers together, 0.64, 0.32, and 0.04, they should add up to 1, which they do. So 0.64 plus 0.32 plus 0.04 adds up to 1. Now what that tells me is what are the odds of getting 2 capital letters as a red flower? It's 64%. So in this population of a garden, for example, in this garden we have red flowers, but what are the kinds of red flowers we could have? We could have a capital R, and the odds of getting 2 capital R's are 64%. Okay, what about these 2 red ones? These 2 red ones, they're red in terms of genotype. They're capital R, little r. But in terms of phenotype, of course, they're still red. So what are the odds of that kind of red? 32%. And the last one, the white flower. What are the odds of getting a white flower? Well, that's only 4%. So 64% plus 32% plus 4% gives me my 100%. So on an exam, they will give you the P, they will give you the Q. And what they'll ask you to do is basically this Punnett square and calculate the P squared, the PQ, and of course you're going to have 2 of those, 2 PQ, and then the Q square down here at the bottom with 2 recessives. And when you do that, you'll get your numbers down here for the genotype, which will be P squared. In this example, it comes out to be 64%. 2PQ comes out to be 32%, and the Q squared turns out to be 4%. And that's how you calculate the genetic frequencies in a given gene pool. Okay? And that will be asked for on the test. Now this is called the Hardy-Weinberg principle. And that is typically what's asked for on the department exam as well.